Welcome, everyone. What we're going to be doing today is we're going to do a summary of some of the famous people that have contributed to the structure of the atom. We can go back to Greek times, ancient Greek times, where many philosophers believed that matter could continue dividing forever and ever without an endpoint. One of these philosophers, which is well known, was Aristotle. It was the belief that you can continue to divide matter in half and then that half into another half, and that it would continue to be divisible in an infinite amount of time. It would never stop dividing. Now, Democritus was a Greek philosopher who disagreed with the others at the time. He proposed that all matter is composed of these tiny, indivisible particles. In fact, he believed that there has to be an endpoint where matter stops dividing. In Greek, the word atomos means indivisible or cannot be cut. From this word is where we get our word atom that we use today. You see, the atom is considered to be the fundamental unit of matter. Now, in this video, we will see that matter is described as being made up of atoms, although the atom is made up of smaller subatomic particles, which are called the protons, neutrons, and electrons. We're going to discuss some of the main highlights as to how the structure of the atom was discovered. We're going to start with John Dalton here, and he proposed what is known as John Dalton's atomic theory of matter. He wasn't even a scientist. He was an English school teacher, although science was his hobby. And he came up with several statements to describe matter in terms of atoms. These statements are known as postulates. Now, the first one is something we take for granted today, and that is that all matter is composed of extremely small particles called atoms. So that's the first postulate. Number two, all atoms of a given element are alike, but atoms of one element differ from atoms of any other element. What this means is that if you're an atom of carbon, that all atoms of carbon are alike. If you're a nitrogen, that means that all nitrogens are alike. But when you compare carbon to nitrogen, since they're different elements, he says that they are different from one another. Now, I will say this. If he were alive today, he would have to modify statement number two. And the reason for that is because the concept of isotopes did not exist at the time. Today, if you compare several carbons, they are not going to be identical. Sometimes you have carbon 12 or carbon 14 or carbon 13, and what makes them different, you'll learn, is that their neutrons are not the same. So today, he would have to actually modify this second postulate. Now, this third one is actually interesting because he was right on the money. It says compounds are formed when atoms of different elements combine in fixed proportions. That's exactly what a compound is. Compounds are made when two or more elements are chemically combined in a fixed ratio. Now, the fourth one, which is also pretty accurate, is his description of what a chemical reaction is. According to his postulate, a chemical reaction is basically the rearrangement of atoms. Okay, if you notice in the example here, notice how hydrogen and hydroxide get together and they form water. And notice how sodium and chlorine get together to form sodium chloride. You have an acid and a base on the left side of the reaction, and then you're making salt and water on the right side of the reaction. You're making something new. What happened is that the atoms simply rearranged themselves. But notice that atoms were not created nor destroyed during this process. In fact, an atom can be defined as the smallest particle of an element that retains the chemical identity of that element. Okay, so we're going to talk about quickly a cathode ray tube. A cathode ray tube was developed or invented by William Crookes, and it's a tube where you pass an electric current, and inside the tube the environment is airless. The air has been removed. It's kind of like a vacuum, so it's at very low pressure. And this beam of current is transparent. However, what he's going to do is he's going to add zinc sulfide inside the tube. And what the zinc sulfide does is it gives it a green fluorescence color when the beam strikes the screen that's coated with zinc sulfide. Now, this beam is called a cathode ray, and in a moment I will demonstrate that it's called a cathode ray because it travels from the cathode, which is the negative electrode, towards the anode, which is the positive electrode. Now, this invention, which was remarkable at the time, was used to project the image in the old TVs before they became flat screens and the old computer monitors. You have a modified cathode ray tube that would produce the image that you would see on the screen. Now, what we're going to talk about is a scientist by the name of J.J. Thomson. What he did is he manipulated the cathode ray. So notice it goes from the cathode here, okay, to the anode. The direction of the beam is always in this direction over here, okay? And let me fix that up. So it's always in this direction over here. Now, the inside is basically, there's no air. It's airless. And because it's airless, you'll see that the pressure is very low. Now, normally, the beam would be invisible, but he coated the interior with zinc sulfide, and that causes it to fluoresce with a green. It looks like a green laser beam. Now, what Thomson did was he manipulated the beam by either using magnets or introducing an electrical plate. And what he saw was that the beam would deflect towards the positive plate. As you can see, it's deflecting over here. And what the conclusion to this is, notice it's deflecting towards the positive plate. That means that the beam over here must be made of some negative character. In fact, I'm going to give you a summary as to his conclusion when he manipulated this beam. You see, J.J. Thomson was able to show that the cathode rays were deflected in an electrical field as well as in a magnetic field. The picture you just saw was showing you in an electric field. The beam bent towards the positive plate because it was attracted to the positive plate, but it also bent that way because it was repelled by the negative plate on the bottom. He concluded that the cathode rays consist of negatively charged particles. He even named these negatively charged particles the electron. So a cathode ray, therefore, is basically a beam of electrons. So J.J. Thomson is credited with discovering the electron, which is a negatively charged particle. Now, he tried to find the individual charge of the electron, but he was not successful. However, he did the next best thing. He was able to find the ratio of the mass to charge the ratio of mass to charge of the electron. And that ratio, which I'll show you here, the mass to charge ratio of the electron is 1.76 times 10 to the 8 coulombs per gram. The coulomb is the official SI unit of electrical charge. So although J.J. Thomson was not able to find the actual charge of the electron, he was able to do the next best thing, which was the mass to charge ratio. Now, Robert Millikan performed an experiment known as the oil drop experiment. In this experiment, he is going to use oil droplets, and he's going to ionize them using X-rays to make them electrically charged. In fact, the oil droplets are going to become negatively charged, and they're going to simulate negatively charged particles or electrons. Now, if you look carefully, there's an opening right over here, and he is going to allow the oil droplets to fall. Now, gravity is going to allow the oil droplets to fall. And what he's going to do, and if you look carefully, the roof up here is a positively charged plate, and the floor is a negatively charged plate. What Millikan is going to do is he can manipulate the voltage of these plates. And what normally happens is these oil droplets are going to fall down. But what he's going to do, and he's looking at everything going on inside, by looking through this opening here. He is going to adjust the voltage so that although gravity is trying to push it down, notice that when a negative approaches another negative, which is the floor here, they're going to repel and it's going to push it back up. Also, notice the roof is positive. So as these droplets are falling, the positive plate will attract the negatively charged particles so that they go back up. So you have two opposing forces. You got gravity pushing down, and then you got the positive plate pushing the droplets back up, and the negative plate also pushing the droplets back up. So what he did was he adjusted the voltage to find a balance where the droplets were suspended in midair, right in the middle. And once that happened, he was able to perform some calculations to figure out the individual charge of an electron. And what he did, which was what Thomson was trying to do, was to find the charge of an electron. Now, the purpose of the oil drop experiment is to find the charge of an individual electron. He found that it was 1.6 times 10 to the negative 19 coulombs. That is the charge of an individual electron. Now, what's very interesting is that if you combine the work of Millikan, which is the charge of the electron, okay, with the mass to charge ratio that Thomson was able to give us, okay, here's the mass to charge ratio, and you use dimensional analysis, you can actually find the mass of an individual electron. Now, the electron is so tiny that the mass can only be calculated through an experiment. There is no balance that exists that can measure something so small. The mass of an individual electron is 9.11 times 10 to the negative 28 grams. And that was calculated by combining the work of J.J. Thomson's mass to charge ratio with Robert Millikan's individual charge by using the oil drop experiment. Now, J.J. Thomson also had a third thing. So we know that J.J. Thomson discovered the electron by manipulating the cathode ray tube. So we know that. Okay. We also know that he found the mass to charge ratio of the electron. And the third thing he did was he came up with a model of the atom called the plum pudding model. And this model was named after a popular English dessert where you had pudding with raisins embedded in it. So I want you to think of this. This is the model. I want you to look at the blue part here. The blue part is like the pudding. And the entire blue, okay, is positively charged. So all of this is positively charged. The little pink circles are like the raisins. In this analogy, the little pink circles are actually the electrons, which are negatively charged. Now, you have a balance here of a positive sphere surrounded or embedded by negatively charged electrons. So this makes the atom neutral. This model was proposed by Thomson. Now, a guy by the name of Ernest Rutherford is going to do a famous experiment called the gold foil experiment. And in that experiment, he wants to see if this model is correct. So I'm going to take you through a brief summary as to how the gold foil experiment was designed and the results of the gold foil experiment. So Rutherford is going to design this experiment, okay, and he's going to use a radioactive source, and he's going to bombard an atom. He's going to use gold, okay, and you'll see gold will be a thin layer of foil consisting of gold atoms will be bombarded with a beam of alpha particles. Now, an alpha particle, which can be represented by the symbol alpha, resembles the nucleus of helium. An alpha particle is literally 2 protons, which are positively charged particles, and 2 neutrons. And if you look at the nucleus of helium, this is the exact same as the nucleus of a helium atom. Now, an alpha particle, the charge of an alpha particle is positive. In fact, it's +2 because it has 2 protons. Now, both a neutron and a proton, they weigh about the same, which they both weigh about 1 atomic mass unit. So the mass of an alpha particle is roughly 4 AMU, 2 protons and 2 neutrons. So it's a pretty heavy particle. Now what's going to happen is we're going to bombard this gold foil here with alpha particles. And if the plum pudding model was correct, all the alpha particles should go straight through. Now what he did, which was very clever, is surrounding the foil, he put a layer, a screen, that did a 360. There was an opening over here for the alpha particles to go through, but the screen completely surrounds the foil. Every time an alpha particle hits the screen, it causes it to fluoresce. It marks it so that it knows where it got struck. Now he expected only this area to be fluorescing, to be showing that it got hit by alpha particles. To his surprise, he saw that there were alpha particles hitting at different angles. They were getting deflected. So the question is, what was causing the alpha particles to get deflected? Well, if you look here, here's the gold atom. Here's our source of an alpha particle. And notice the majority of the alpha particles do go through. There were only very few deflections. Not many, but there were some deflections. So here's what he proposes. He basically says that the plum pudding model is incorrect because if that model were correct, there should be no deflections. It should all go through. So what causes the deflections? Now think about it. An alpha particle is positive. The only way to deflect a positive is if a positive meets another positive. Now gold is an atom that is pretty big. It has an atomic number of 79, which means it has 79 protons. An alpha particle is much smaller. So if you have gold atoms right over here, the only way that the alpha particle would be deflected is if it met these 79 protons. So look what he proposes. If we look at gold, if we magnify it here, he says that all the positives are found in a very tiny region that he's going to call the nucleus. Okay? So he says that all the positives, all the protons are in there. So when an alpha particle gets near the nucleus, it's a positive is getting close to a positive. Now remember, the alpha particle only has a mass of 4 AMU. A gold atom is much heavier. So the one that's going to deflect is the alpha particle, not the gold atom. It's much smaller. So notice that when you have a alpha particle getting near the nucleus, notice how it gets slightly deflected here. Here it actually hits the nucleus, so it gets completely deflected. And to him, these deflections, okay, were the result of a positive meeting a positive. Now, if the plum pudding model were correct, all of the lines that you see here, all these red lines, would have gone through, and that was not the case. Okay? Now, here's the other thing. Part of his conclusion is that the nucleus must be tiny compared to the rest of the atom because only very few alpha particles got deflected. Most of them went through. And the reason most of them go through is because the atom is basically empty space. The majority of the volume of an atom is empty space, where you will learn that that's where the electrons are found. We call that the electron cloud. So notice that Rutherford came up with a new model. He scrapped the plum pudding model and came up with this new model called the nuclear model of the atom. Now let me show you a little conclusion here. If we go back here, okay, Ernest Rutherford concluded that all the positive charge, which are the protons, and basically all the mass of an atom is concentrated at the center of the atom in a very tiny core called the nucleus. Notice that we mentioned earlier how the electron has no mass practically, so that's why nearly all the mass of the atom is found in the nucleus. Now, the nuclear theory of the atom was proposed way back in 1911. He did this experiment in the early 1900s. And again, the main component of the nuclear theory of the atom is that all positive charges and nearly all the mass of the atom is concentrated in this tiny, tiny nucleus. The negatively charged electrons, which basically have no mass, they're the ones found outside the nucleus. Now, they're also the ones that occupy nearly all the volume of an atom. Based on the results, because you are seeing, and you'll see back over here, since most of the alpha particles go straight through, okay, you'll notice that the majority of the volume of the atom is basically empty space. See how most of them do go through without any deflections. Now, those few that got deflected is because they went close enough to the nucleus, and when the positive met the positive, it caused them to deflect in one angle or another. Okay, so here is, and there's the plum pudding model that we just disproved. This is probably a better comparison. Had the plum pudding model been correct, this model proposes that the entire atom is neutral. So he would have seen no deflections. Everything would have gone through. Now notice, here's a sample of one, let's say one individual gold atom. Notice that the nucleus is tiny. So only 2 deflections here in this example, because since the nucleus is so small, only very few alpha particles get deflected. Since the majority of the atom, look at the volume here, since it's mainly empty space, that empty space is the electron cloud, that explains the fact why most of the alpha particles went completely through. Okay? Now, there was something else that he could not explain. It was discovered later. There is another subatomic particle in the nucleus. The mass that he calculated, he was really off. He only accounted for the mass of the protons, and he didn't know what else was in there contributing to mass. A guy by the name of James Chadwick discovered that there was another particle in the nucleus of the atom that has about the same mass as the proton. However, this particle has no charge. It's neutral. And James Chadwick basically discovered the neutron. Okay, so when we look at an atom today, think of it as a big sphere. The nucleus is very tiny compared to the rest of the atom, and in this nucleus is where we find the protons, which are the positive particles. Okay, and we also find the neutrons, which James Chadwick discovered that those are neutral particles. And then the majority of the volume of the atom, okay, is the electron. And the electron, basically, they're the negatively charged particles, and they occupy this empty space, which we call the electron cloud. So the atom consists of these 3 subatomic particles in this arrangement. Now, if you want to know what the mass of the atom is, the mass of the atom is basically just the sum of the protons and the neutrons. The electron's mass is so little that it's negligible, and it's not used as part of the calculation to figure out the atomic mass. So this is a quick summary of some of the main experiments, okay? Starting with, William Crookes inventing the cathode ray tube, then J.J. Thomson manipulating the tube, using it to discover the electron, and then we saw how Millikan was able to, using the oil drop experiment, he pretty much found the charge of an individual electron, which was something Thomson wasn't able to do. And then Thomson did propose the plum pudding model, but that was discovered to be wrong by the experiment done by Ernest Rutherford, known as the gold foil experiment. And finally, James Chadwick was able at a later time to discover a 3rd subatomic particle that is neutral and found in the nucleus, which is the neutron. Okay, so that hopefully will summarize some of these main scientists.